show that simple pendulum performs linear accretion. Simple pendulum performs linear accretion, hence derive expression for its time period. So that simple pendulum performs linear accretion, hence derive expression for its time period. If I can prove acceleration is proportional to displacement and directed opposite to the displacement, then we say simple pendulum performs linear accretion. That means if it satisfies the definition of SHM, it will perform linear accretion. Hence derive expression for its time period. Any periodic motion time period is always 2 pi by omega. Now for SHM, F is kx. That means MA is m omega square x. So a by x will become omega square. So root of a by x will be omega. This is how we can find linear SHM's time period of pendulum. If I can find a by x, then taking square root. So first step, show that simple pendulum performs linear SHM. Then derive expression for time period. Heading written.
Yes, sir.
Slowly we are doing thoda lengthy proof hai ye. A small metallic sphere called as bob suspended with the help of light inextensible string. A simple pendulum consists of small metallic sphere called as bob suspended with the help of light inextensible string from rigid support at point O. So what is simple pendulum पूछा तो इतने लिख रहे हैं. A simple pendulum consists of small metallic sphere called as bob suspended with the help of light inextensible string. I am doing the derivation. Consider simple pendulum consisting of small metallic sphere called as bob having mass m suspended with the help of light inextensible string of length L from rigid support OA be the equilibrium position. मतलब यहाँ पे वो net force 0 हो जाए. Let the pendulum be given small angular displacement theta and released. It performs oscillation on both sides of equilibrium position. Let x be the linear displacement. At displaced position B, forces acting on the bob are its weight mg vertically downward and tension T along the string. And tension T along the string. Weight mg can be resolved into two rectangular components. Can be resolved into two rectangular components. This is theta. Theta ka बाजू वाला is mg cos theta and the other one is mg sin theta. The pendulum is given small angular displacement theta and made to perform. एक सेकंड फिर से इधर स्टार्ट करता हूँ. Diagram you have followed?
Yes, sir. Yes, sir.
Everybody has followed ना पक्का?
Yes, sir.
हाँ, अभी डायग्राम का थियरी पहले. Simple pendulum consists of small metallic sphere called as bob having mass m, suspended with the help of light inextensible string from rigid support having length L. The pendulum is given small angular displacement theta and released. It performs oscillation on both sides of equilibrium position. Let x be the linear displacement. At displaced position B, at displaced position, forces acting on Bob are: first, its weight mg acting vertically downwards. Tension T along the string. Weight mg can be resolved into two components: mg cos theta along the string, mg sin theta perpendicular to the string. Now draw the diagram till this. Just draw the diagram, don't write anything. Done? Diagram?
Yes, sir.
Right. Consider a simple pendulum. Consider a simple pendulum consisting of consider a simple pendulum consisting of small metallic sphere called as bob having mass m to be suspended with the help of light in extensible string called as bob having mass m to be suspended with the help of light in extensible string from rigid support at inextensible string of length L from rigid support at point O. Let OA be the equilibrium position. Let OA be the equilibrium position.
Done, sir.
Let OA be the equilibrium position. Next paragraph. The pendulum is given small angular displacement theta. The pendulum is given small angular displacement theta and released. Small angular displacement theta and released. It starts performing oscillations on both sides of equilibrium position. It starts performing oscillations on both sides of equilibrium position. Let x be the linear displacement. Let x be the linear displacement. Then copy here from here. At displaced position B, Full copy till weight mg can be resolved into two rectangular components, mg cos theta along the string and mg sin theta perpendicular to the string.
Yes, sir.
Completed?
Yes, sir.
Okay, everybody is done?
Yes, sir.
Okay. अभी कौन सा स्ट्रिंग है ये? इनएक्सटेंसिबल है ना?
Yes, sir.
मतलब mg cos थीटा इसको आगे खींचेगा क्या?
No, sir. It can't.
तो टेंशन पीछे खींचेगा क्या? कुछ भी नहीं होएगा ना इसको, धागे को?
नहीं सर.
कभी होगा ऐसा नहीं, जब ये दोनों बैलेंस कर लेंगे ना,
Yes, sir.
तो खाली अनबैलेंस्ड फोर्स यही बच गया ना, mg sin theta.
Yes, sir.
So it was trying to bring the body back, no, this way.
Yes.
What is name of that force which tries to bring the body back?
Restoring force.
Restoring force. So since the string is inextensible, hence tension T balances mg cos theta. Thus, the only unbalanced force is mg sin theta, which tries to bring Bob back to its original position. Therefore, restoring force, F equals to minus mg sin theta. Negative sign indicates that force is directed opposite to the displacement. चलो इधर का कॉपी कर लो जरा. हाँ, मैं नेक्स्ट वीक का पूछ रहा हूँ. आज का लोएस्ट कितना है? अभी 98 है. या 85 पे एक इसी को बचा उससे घर में आएंगे. 85 है. 8521 में कुछ नहीं है. इन्फोसिस कितना है? नहीं अपना ये कैश है. ये पूरा निकाल दो. 50 है। फिर आ जाएगा ना इधर। अच्छा, तो भाई ना, तो अपना ये 12 कितना, 12 2 3, नहीं वो तो 29% हो गया। तो ये पूरा निकाल के आएगा अपने को। नहीं तो जान दो, चलो जान दो, जान दो। हेलो,
Yes, sir.
completed till that? Just complete full?
Yes, sir.
What, completed?
Yes, sir. Completed.
अच्छा अच्छा। The string is inextensible and tension-free balances mg cos theta thus mg unbalanced forces mg cos theta. Mg sin theta tries to bring the bob back to the original position. Restoring force is minus mg sin theta. Negative sign indicates that force is directed opposite to the displacement. Can I clear now this?
Yes, sir.
अभी इसके बाद एक्चुअल प्रूफ चालू हो गया, मतलब इधर तक डिस्क्रिप्शन डायग्राम भी डेड. Since theta, if theta is small and measured in radians, then can I say sin theta is approximately theta? Are you aware of this?
Yes, sir.
नहीं मालूम है तो बोलते जाना, मालूम है तो I will proceed ahead. If theta is small and measured in radians, sin theta approximately theta can be right.
Yes, sir, we can.
Yes, sir.
So F becomes minus mg theta. Then let A be acceleration in, let A be the acceleration in the bob. Therefore F equals to ma. So ma equals to minus mg theta. That means A equals to minus g theta. Okay, just copy till this much. If theta is small and measured in radians, sin theta approximately theta, F equal to minus mg theta. Let A be the acceleration in bob. Therefore F equal to ma.
Done, sir.
If this is circle, what is this part called as?
Arc.
Arc. This is theta, this is radius. What is relation between these three?
S is equal to R theta.
R theta.
Is equal to r theta, perfect. In our pendulum, can I assume this is like arc?
Yes, sir.
So if this is theta, this is length, and this is x. In this is arc, this is radius, and this is theta or not?
Yes, sir.
So we can say we know that arc length equals to radius into angle. So arc length is x, radius is L into theta. So theta is x upon L. Therefore, A equals to minus G x upon L. Since G, comma L are constants, therefore A equals to minus constant into x. So A proportional to minus x. This shows that simple pendulum performs linear oscillation. Now from here complete. Yes, done now?
Yes, sir.
Okay. So this shows that simple pendulum performs linear resection because A we are getting proportional to minus x. Now time period of simple pendulum. Since A equals to minus gx by L, so A equals to gx by L in magnitude. From this A upon x equals to g by L. Now time period capital T is 2 pi by omega. 2 pi upon root of A by x. So time period is 2 pi root of A by x. I explained how omega will become root A by x. G by L. So T is 2 pi root L by G. This is expression for this is expression for time period of simple pendulum. T is 2 pi root L by G is time period of simple pendulum. Solve. So we got simple pendulum performs linear section plus we proved that time period is 2 pi root L by G. Done.
Done, sir.
Define seconds pendulum. Define seconds pendulum. A simple pendulum whose time period is 2 seconds is called as seconds pendulum. So simple second pendulum is also simple pendulum, but it is having specific time period as 2 seconds. For a simple pendulum, we know time period is 2 pi root L by G. Therefore, for seconds pendulum, time period will become 2 seconds. So we can say 2 equals to 2 pi root L by G. 2 cancel. 1 equals to pi root L by G. Squaring both sides, we get 1 equals to pi square L by G. Therefore, L equals to G upon pi square. This is expression for length of seconds pendulum. So they can also ask derive expression for length of second pendulum. So this is how we can get expression for length of seconds pendulum. Yes, clear?
Yes, sir.
Simple, na? Time period is 2 seconds is second pendulum. Then in time period for 2, you will get length as G upon pi square.
Yes, sir.
2 delay. आपको स्टार्ट नहीं HDFC आएगा क्या सर? अच्छा, हाँ वो तो हार्डली बात है, तो उसको निकाल दे। अच्छा, एक बार खाली डाल के देखते हैं। नहीं, HDFC बैंक आता है क्या देखते हैं। 10 10 10। अच्छा, तो 8 आ जाए। 8 आ जाए। पांच दे पांच दे पांच। अच्छा हाँ ठीक है, तीन लेते हैं अपन। Can I clear this now?
Yes, sir.
Right. Laws of simple pendulum. So next class, this chapter will get over with some MCQ. Tomorrow I have kept extra lecture. Time I think I have told you all, na timing. Tomorrow
No, sir.
9 o'clock convenient, 9 to 10, one extra lecture evening.
Yes, sir.
Just check everybody, is it convenient? One extra
Sir, can you keep it a bit early?
tomorrow, bit early you want?
8:30.
8:30 I can keep. 7:30 also I can keep. 7:30 will do.
Sir, 7:30 we are till 7:30. Sir, I guess we are having our maths class till 7:30.
Today maths is there, na? Tomorrow is Thursday.
Yes, but he's also keeping extra lecture for CBSE students for that statistics.
Acha, acha. So, acha, morning time you all are not free. Morning.
No, sir, we have our college.
So just give me 8:30 वाला time. चलेगा 8:30 to 9:30.
Okay, sir.
Yes, sir.
Possible? Can I lock it?
Yes, sir.
Okay, चलो ठीक है ठीक है. Laws of simple pendulum. First, see we got time period as 2 pi root L by G. So if I take bob of different masses, 1 kg, 2 kg, 3 kg, किसका टाइम पीरियड ज्यादा होएगा?
सर 3 kg वाला।
नहीं, सबका टाइम पीरियड सेम भी होगा ना. टाइम पीरियड पे किधर डिपेंड करता है बॉब का मास?
ओ हाँ सॉरी सर, मैंने लेंथ को सोचा, सॉरी।
The time period does not depends upon mass, correct? So whether you take
Yes,
bob
sir.
of 1 kg, 2 kg, 3 kg, कुछ फर्क नहीं पड़ेगा. तो पहला लॉ, टाइम पीरियड of simple pendulum, time period of simple pendulum is independent of mass of bob. Second, it is directly proportional to the square root of its length. Directly proportional to the square root of its length. Third, it is inversely proportional to the square root of acceleration due to gravity. Inversely proportional to the square root of acceleration due to gravity. Complete 3 point. One more we have tried. First 3 point completed.
Yes.
Fourth point, right? It is independent of amplitude of oscillation. It is independent of amplitude of oscillation. Next study. Damped oscillations. See, whenever word damp is given, that means opposition. So damped oscillation means somebody is opposing its oscillation. If this is suppose pendulum oscillating like this about mean position, if somebody is opposing it, then can it move with same time period? क्या ज्यादा टाइम लगेगा उसको मूव करने के लिए? हेलो हेलो,
Yes, sir.
इज द बॉडी, ये इधर आ रहा है, कोई तो उसको पुश कर रहा है ऐसा उल्टा, तो आ सकता है क्या फास्ट? टाइम लगेगा ना इसको आने के लिए फास्ट,
Yes, sir.
मतलब टाइम पीरियड बढ़ जाएगा ना, ज्यादा टाइम लेगा, और इसका एम्पलीट्यूड भी धीरे धीरे कम होने लगेगा, ऐसा कम होने लगेगा. So whenever body is oscillating with same amplitude throughout, same amplitude, then it is called undamped. आईसीएससी वाले स्टूडेंट को लास्ट ईयर था ये थोड़ा सा, बट अगर इसका एम्पलीट्यूड कम 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 हो रहा है तो उसको बोलते हैं डैम्प्ड ऑसिलेशन. So the oscillation with decreasing amplitude, the oscillations with decreasing amplitude due to opposing forces called as damped forces is called as damped oscillation. The oscillation with decreasing amplitude due to damped forces, the oscillations with decreasing amplitude due to damped forces, in bracket you can write opposing forces, is called as damped oscillations. So in damped oscillation, amplitude will go on decreasing. The oscillations with decreasing amplitude due to damped forces is called as damped oscillation. Done?
Done.
Okay. So that's all for today. Just 1 hour more topic is left out to complete the theory. Tomorrow we'll complete.